everyone. I'm Lindy Elkins-Tanton. I'm the director of the School of Earth and Space Exploration at Arizona State University. My son Turner and I were standing on a causeway next to an estuary in coastal Florida as the sun was rising, and we were peering through binoculars at the launch pad at Cape Canaveral, where they were about to launch the MAVEN mission to Mars. And even from where we were a number of miles away, the launch was absolutely breathtaking. And the hair stood up on the back of my neck, and the rocket engines ignited with the roar of 1,000 race cars. And then Turner and I turned to each other and we said almost at the same time, I really hope the next launch we come to is ours. Because I'd come to this amazing moment in my life where I was proposing a mission to NASA. And had I imagined that I was going to do this when I was a student? No, I had never imagined that. Unlike a lot of the scientists who were working on the MAVEN launch, I had not gone straight through in science. After my master's, I worked in business for 8 years. I worked as a management consultant, and I did financial forecasting for US News and World Report. And I wrote business plans for young high-tech ventures looking for investment. And then I taught math at a liberal arts college for 2 years before I went back for my PhD. And I started my PhD at age 31 as a single parent. I had been investigating different areas of human endeavor, trying to figure out which one had the most meaning for me. And in the end, academia has given me both the opportunity to ask the biggest questions and also the schedule flexibility to stay deeply connected to my family. And so now I'm a planetary scientist trying to understand how rocky planets like Earth get their structure, how they're built, and also what makes them habitable. And the best way to understand Earth is in the context of the other rocky planets in our solar system, Mercury, Venus, and Mars. And that requires space missions. So why do we explore space? First of all, because exploration is a human imperative. It's built into us. Everything from Magellan to Captain Janeway. And exploration aligns humankind looking outward instead of allowing us to be distracted by the irritations that lie between us, both as people and as nations. And for me personally, I'm really interested in the asteroids and the small bodies that lie among the familiar planets of our solar system, because they're the leftovers of planetary formation early in the solar system. And so by studying them, we actually travel back in time to study the processes that built the planets. And then we can take that information with us while we investigate planets around other stars, exoplanets. But not every institution can do this kind of big science, can try to answer this kind of big science question. It requires a dedication to interdisciplinary work, and it requires a patience with the long timelines that big questions require. And it also requires a positive, collaborative, teamwork kind of culture. And a lot of institutions don't have that, but we have that here at ASU. And making progress in science requires new observations. Every time we send a mission into space, we get surprises. The solar system surprises us and gives us things we don't anticipate every time we send a mission out there. Think of the New Horizons mission to Pluto and the amazingly detailed images we have of Pluto's surface for the first time ever. There were a lot of us who thought that Pluto was going to be a bit of a yawn. We thought it was going to be sort of a dirty ice ball. But these images show us smooth areas on the surface and mountains and features that indicate that Pluto was a warm, active planet much longer than we had anticipated. And so in the summer of 2012, I found myself at the Jet Propulsion Laboratory designing a space mission. Some people at JPL had read a paper that I'd written, and they wanted to design a mission to test it. So who could resist that? We were in a room called Leftfield, which is lined with whiteboards and shelves that have construction toys and Legos and Post-it notes and markers, and it is a playground for creativity. In fact, when we walked in, we found some Post-it notes that had been left by the previous mission planning session. It's a very effective room. And I was there with about 10 of my favorite science friends planning a space mission to help us understand how rocky planets get their structure. So our familiar planets, Mercury, Venus, Earth, and Mars, have an iron nickel metal core and a rocky exterior. But how and when do they get that structure? Planets are born as gas and dust orbiting the infant sun And in just 1/100th of the age of the solar system, they build up into the familiar planets that we see, these differentiated bodies with iron, nickel, metal in the middle and rock on the outside. So we decided that the best place to investigate this process is the asteroid Psyche. Psyche is a small world that seems to be made almost entirely of iron, nickel, metal. Imagine that. Humankind, we have visited through space missions rocky planets and moons and icy moons, and we've visited planets that are made of gas, but we have never seen a metal planet. We do not know what this will look like. Psyche is out between Mars and Jupiter, and it's never been visited, and we've never had an image of it that's more than just a point of light. So this would be true exploration and true discovery. So what might Psyche really look like? Could its surface be covered with sulfur lava flows? Could it have towering fault scarps that were created when the hot liquid metal froze and shrank and the exterior of the body broke into scarps, fault scarps? Could its surface be a glittering combination of iron, nickel, metal, and green crystals, the way some iron meteorites are that have fallen to Earth? And what would an impact crater into a metal surface look like? We've never seen one. Could the splashes or the edges freeze in the cold of space before they fall back onto the surface of the body? We think Psyche is the metal core of a small planet that was destroyed in the high energy, high speed first 1/100th of the solar system's time. It is the only way that humankind can ever visit a metal core, because Psyche is the only body like it in the solar system, and we can never go to the Earth's core. The Earth's core lies at about 3,000 kilometers depth, but the farthest that humans have ever drilled into the surface of the Earth is just 12 kilometers. And the surface of the core, deep inside the Earth, has a pressure about 3 million times air pressure that we have around us right now. And the temperature is about 5,000 degrees Celsius, which is approximately 10,000 degrees Fahrenheit. So we are never going to go there. But Psyche gives us a chance to visit inner space by visiting outer space. So about 40 of us teamed up, and we wrote this proposal in concert with Jet Propulsion Laboratory and Space Systems Loral. And the Psyche mission proposal has just been selected as a finalist in this round of selections. We hope to go to Psyche and orbit for a year, learning how rocky planets are built. Science makes progress in increments, and we try to make them the biggest increments we can on the way to answering that biggest of all science questions, are we alone in the universe? And so please cross your fingers and cross your toes that when the announcement is made in the fall of 2016, Psyche is chosen for flight, and then we can stand on that causeway and watch our mission get launched into space. And just like science, people make progress in increments too. You never know the skills that you're going to gather along the way that make it possible to fulfill a vision. And every vision starts with a moment of inspiration. Sometimes it's an image that's just a point of light in space. Sometimes it's as simple as a pile of Legos or a Post-it note, like the ones that we found in the Leftfield room when we went in to plan our own mission. Thank you very much.